Lynn, I need you to say that again.
I think my dice was rigged. I got a lot of sixes to begin with.
Okay, hold that thought. You hear what you just said? I think my die is rigged because I got a bunch of sixes. Did I tell you guys about the email I got? I probably didn't because I think I got it yesterday. A former student sent me an email from Spain. I don't know if I told you about this. I don't think I did. Former 243, 244 student, so former stat student, has an iPod, and there was 449 songs on it, right? 5 of them were Keisha. I asked why. She didn't answer me. 28 were John Mayer. Easy. So, she said while she was listening to her iPod on shuffle, she got Keisha, John Mayer, Keisha, John Mayer, Keisha, John Mayer all at once, like in one big block like that. And she said, what's the chance of that happening? Which is the same thing I hear all the time whenever I say, oh, that's my birthday too. What's the chance of that happening? The answer is pretty good, actually. Yeah. It's pretty good that will happen. Now, what she was saying was, but it's 6 songs. There are so few Keisha and John Mayer songs. Why would they all be together? And I said, yes, but you have 449 total songs you're playing through. And chances are you've played through that set list more than once. Do you remember yesterday when we had hundreds of coin flips on the board? Weren't there some runs of heads and tails that were like 8, 9, maybe even 10 long? It's gonna happen somewhere. So I love this statement, Lynn, because it goes against how we're programmed as humans. We roll dice 10 times. We expect kind of an even spread of 1s, 2s, and 3s, and 4s, and 5s. And when we get too many 6s, we say, it's rigged. But I think what we're going to see is as we spread this out over the entire course, an evening. Yes. That's what we're going to get around to, eventually understanding the definition of 1/6 empirically, not classically. Classical's great, except it doesn't exist in reality. You need to experience it empirically. So let's collect some data. What I've done up here on the board, I'm going to do a couple of these. I need to count first. You all spun 10 times, right? So I got 1, I didn't do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is done. We'll just count it up when we're done. Let's go around the room. Let's do some addition. How many of you got 1s? Raise your hand and show me with fingers how many 1s you got. Show me with fingers how many 1s you got. So we got 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 26, 30, 34, 38, 43, 44, 45, 46, 47, 48, 49, 50. We got 50 ones.
Wait, did you mean all together?
Out of the 10.
Out of the 10. Then you need to add 6 to that.
You got 6 ones.
I got 6 ones.
56. What do you think, Lynn? Is her die broke too? Broke in?
Okay. And I got 4 1.
So we got 60 altogether.
Did you guys roll 10 times or 20 times?
It doesn't matter, because it's going to show up here. That's why I stopped counting you, because this way what I'll do is I'll just add this up and I'll know how many rolls we had. It saves me ever me trying to deal with it, yeah, because I'm probably going to be wrong no matter how I count. I'm probably going to be wrong here. I'll be off by 1 or 2 because I'm counting and because I can't count. All right, 2s. Same thing with 2s. Same thing with 2s. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8, 12, 16, 17, 18, 20, 3, 24, 25, 32, 36. 36 twos. All right. 3s. How many 3s did we get? Show me with fingers how many 3s we got. How many 3s did we get? How many 3s did we get? All right. This is fantastic. 5, 7. How many is that? Now, keep track of your phone. I can't count. Oh, there we go. That's 9, 10, 11, 14, 20. Wait, how can you have 6 1s and 6 3s?
You know what I did?
You rolled more than 10 times.
I rolled 2 dice. I looked in.
Oh, got it. Sorry. 3s again. I lost count. 3s again. Hey, don't apologize. It's okay. Give me 3s again so I can count again. I'm sorry. 3s again. 5, 7, 11, 12, plus 6, correct? 18, 20, 3, 25, 29, 33, 38, 39, 40, 41, 41 plus 7, it's 48. There's 48 in there. Beautiful. 48's in there. Okay. 4s. How many 4s did we get? How many 4s did we get? Okay, we got some 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14, 19, 26, 28, 30, 3, 38, 46, 51, 54. 54 right there. Let's do 5s. do fives. We got some fives.
Hold on.
We'll start on this side. We have 4, 6, 8, 12, 14, 18, 19, 20, 2, 27, 29, 34, 36, 37, plus 5 is 42, 44, 45, 46, 51, 52, 55, 7, 9, 62. And let's call these sixes. Sixes. How many sixes do we have? How many sixes do we have? This is where Lynn broke her dice. Broke her die, I should say. 1, 2, 3, 4, 7, 8, 10, 14, 15, 16, 19, 21, 25, plus 3 is 28, 37, 41, 45, 46, that was 3, 46, 47, 52, 57, 59. Beautiful.
So Sean, I just
Yes.
voted for my invisible friend.
You voted for your invisible
I
friend?
wrote for my invisible
Oh, good. So we have another person that's just not here but is here.
Yeah.
And it doesn't matter to me anyway. It doesn't matter to me anyway because I don't really, it doesn't bother me that we had some people maybe rolling more than 10 or fewer than 10. I was trying to keep it at 10 because originally what I was going to do was go around, count you all, and multiply by 10. And then I realized all I really have to do is add this up, and that tells me how many times we rolled. Does that make sense? So I was overthinking it, basically. So let's figure that out. And if I did it right, it should end in a 0. I probably won't have done it right. 60 plus 36 plus 48 plus 54 plus 62 plus 59 does not end in a 0. It's close. 319.
I think you need to add 1 3. I think I put up one finger and meant 2.
You said I actually added correctly?
Yes.
So this is 49?
Yes.
Thank you, Kate. 49, this is 3. I find that hard to believe that I added correctly.
I don't.
I prefer to think that I screwed up symmetrically. And my pluses and minuses canceled. We'll give me credit. We'll give me credit for 320. All right. So when I say n equals 320, what I'm trying to do is get you guys used to the idea of statistics. So when you, for example, read a scientific journal, if you read a scientific journal, you'll often see this little lowercase n, or you'll read a Gallup poll or Quinnipiac poll, like when they talk about presidential hopefuls and their popularity ratings, or when you hear a statement like Congress is less popular than syphilis. At the bottom of that, they'll actually have a sample size that they sample. And they often use the letter N. So we did 320 trials. So, did you hear about that one?
The N stands for trials.
Number of trials. We rolled 320 dice. If you think about it that way. It's almost like one person taking 320 dice and going whoosh, and then counting what happened. That's what you guys just did, but you did it 10 at a time or 20 at a time. Fair enough? Okay. Question. How many ones should we have gotten out of 320 rolls?
1 out of 6.
We would go for 1 out of 6. So how many ones would that be?
53.
It might not be a sensible number because it's an average. Kelly, go ahead.
Would you just divide 60 by 320?
Other way around. 320 by 6.
Yeah.
So out of the 320 rolls that we did, let's do it this way. 1/6 of the 320 should be ones. If these dice were behaving perfectly classically. Perfectly classically. Does that make sense? Perfectly classically? 1/6 of the 320 should be 2s. 1/6 of the 320 should be, and so forth and so on. Ditto. And what does that come out to be? 53.6666? Is that what it is? 0.333. Thank you. 2/3 or 2/6, not 4/6. So I get 53. Let's call it 53.3. How's that sound? Because it's going to repeat forever anyway. So we should have gotten on average 53.3 of each of these. Does this make anybody's gut turn a little bit?
Yeah, that ain't gonna happen.
Well, it can't, correct? You can't roll 53.3 ones. You can roll 53, you can roll 54, but you can't roll 1/3 of a 1 or 1/3 of a 2 or 1/3 of a 3. And the reason for this is an average. I've drawn a little red line between expected and the word statistics over there. On average, you would expect to get 53.3 per 320 trials. I want you to think of this like you thought of slope back in the day. Watch this. You ready for this? This gets good. So, 50 on average or an expectation an expected 53.3, it doesn't matter to me, we'll say 53.3 ones per 320 trials. It's a rate. It's a rate. Out of every 320 trials, we're going to expect 53.3 ones. Now, I know you're sitting there going, that doesn't make any sense. You can't average 53.3. I'm like, yes, you actually can. You can't roll 53.3, but you can average it. If that's making you sick to your stomach, don't worry. It's 533 ones per how many trials? Pretend you're European for a second. Right, yes, you're now European. What will 53.3 be if it was per wall? How did I get from there to there? What did I do?
30,200.
Say it again.
3,200.
3,200 trials. Very nice, yes. Yes, wonderful. So essentially, it's simply an average. It's simply an average. 53.3 per 320 is the same as 533 per 3,200. It's just the slope like it was before. Put it over any denominator you want. So if the decimal is upsetting you, simply bump the decimal out until there's not a decimal there. Does that make sense? Totally. That's how you have to think of it. It happened back in the 90s. The first time this ever made sense to me, once again the lights are off. The first time this ever made sense to me was when I saw the results from the 1990 census. On average, 1990, there were 2.5 children per family in the U.S. 2.5 children per family. And the joke, oh, it was a kid, blah, blah, blah. No. 2.5 children per one family is the same as 25 kids per 2.5 children per one is the same as 25 kids per 10. Just move the decimal. Make 2.5 25. How do you do that? You multiply it by 10. So change the 1 to 10 by multiplying by 10. If the fraction's value is the same. It's the same as 1 over 2. It's the same as 10 over 20. It's the same as 20 over 40. They're all 1/2. So just make it so there's no decimal. That's the same value. Does that make sense? Believable, fair? And we're going to see how this maintains. We'll see how this maintains as we play today. But the first thing I want to do is I want to drive a point home from you guys. I did an observed column and an expected column. What I want to do is I want to do something called percent error with you. I've had you guys do this before in your homework. I'm going to have you do it again for next class. And probably I want to revisit this idea over and over again because I think it's helpful to see what happens to percent error, to precision, if you will, of data as sample sizes grow. I want to look at the percent error between what we saw. I should have this over here, actually. I want to look at the percent error of the data that we saw versus the data that we were expecting to see. And basically, the idea of percent error is you take your observed value minus your expected value, and you divide that by your expected value. Right? So let's all do that. Let's break this up. Let's have this row right here. You guys compute the percent error for this one. Next row back, you guys do the percent error for this one. This is 36 minus 53.3 over 53.3. Make sure you get the sign correct, too. Some of these are going to be positive, some are going to be negative. Can you back both rows over there? Can you guys handle threes? 49 minus 53.3 over 53.3. You guys up here, this Brandy in this back row right here, can you guys handle 4? 54 minus 53.3. Yeah, that's a minus. Over 53.3. Next row back, can you guys handle the 5s? That's 62 minus 53.3 over 53.3. And the guys in the back there, you guys handle the 6s, which would be 59. I know. Minus 53.3 over 53.3. Let's get 6% errors. And I know this seems like a silly exercise. This seems like a silly exercise.